I'm Alyssa Welch. I'm the program manager for the Midwest CASC and part of the Midwest CASC consortium staff hosted here at the University of Minnesota. Thanks to folks who are joining us for the first time for our science seminar, and to those folks who are already familiar with our work. And as always, a really big thanks to Jess Del Fiacco, our communications manager, for organizing the session, as well as to our speakers and guests joining us today. Please note, like always, that this presentation is being recorded. So please adjust your video settings accordingly and mute your microphones throughout the session. And if at any point you have questions, feel free to add those to the Zoom chat. We'll generally hold the speaker questions until the end, unless there's a pressing point in the middle. All right, next slide. Thanks. Before we begin, as always, I'd like to provide a very brief background on the Midwest CASC as a reminder of the importance of our regional research projects and collaborations. The Midwest CASC is a partnership between the USGS, the U.S. Geological Survey, and a consortium of institutions across the region, as you see here on the map, hosted by the University of Minnesota. We're part of a national network of regional CASCs, all working to provide science that seeks to inform research management efforts that help fish, wildlife, water, land, and people adapt to a changing climate. We work on topics specific to our Midwest region and Midwest regional management priorities in several ways, including conducting synthesis research projects on relevant regional topics, supporting a network of interns, graduate students, and postdoc fellows. We support a broad network of USGS-funded climate adaptation projects and researchers. And we also host technical workshops and an annual gathering of the Midwest CASC community. Next slide, please. In fact, our two announcements today include that we are 1 week away from our August Summer Science Symposium here in the Twin Cities. If you've been following for a little while, this is the first time that we get to host here in the Twin Cities at University of Minnesota, and we are very excited to host a large group of people who have registered. In fact, we've reached our room capacity limits. So if you're registered, you're in a good spot. If you'd still like to register and like to go on the wait list, I believe the link is still available for that. And we are also really pleased to share that we are hosting a science communication technical session on September 30th. This is open and available to anyone in our Midwest CASC community. The link is going to go into the chat here as a direct registration link. So feel free to sign up for that if you are interested in that topic. We hope you are. All right, I now have the pleasure of introducing our speakers for today. I am going to introduce, three gentlemen who have joined us here today. One speaker and two supporting guests who will be assisting with answering the questions, all three of whom have worked on this really amazing project that we're going to be hearing more about today. First, Dr. Famara Damfa is the Center Director at the University of Minnesota's NatCap TEEMs Research Center, of which he's also the co-founder. He is committed to fortifying NatCap's partnership with stakeholders at local, regional, and global levels, aiming to advance natural capital accounting and ecosystem service valuation for informed decision-making towards a sustainable future for all. Dr. Damfa will be our primary speaker for today. We also welcome Dr. Philip Adalaku, postdoc researcher with University of Minnesota's NatCap TEEMs Research Center, who holds a PhD in civil and environmental engineering from South Dakota State University, with a specialization in water resources engineering. His expertise includes watershed management and the design of climate-smart mitigation strategies, and he has significant experience in hydrologic and hydraulic modeling, agricultural water conservation, and natural capital and ecosystem-based adaptation. Finally, Dr. Heyman Lohano joined the NatCap TEEMs in February 2025 and has been engaged in the Global GEP project. He's currently a visiting professor in the Department of Applied Economics at University of Minnesota and is a professor at the Institute of Business Administration in Karachi, on leave since January 2025. I will now pass it over to our speakers so they can tell you more about their project today. A reminder to adjust your video settings accordingly and be thinking about those questions for our Q&A session at the end.
Sorry, I gotta start with unmuting because when I project, I can't unmute. So apologies for that. So can you still see the screen or no?
You're not in presentation mode yet.
Okay, let's do
if you're able to do
presentation
that.
mode.
Perfect.
That looks great.
Perfect. Well, thank you very much, Alyssa, and very much thanks to the Midwest Cast for inviting us to the science seminar to present on this incredible work. What really excites me about this work, it all started with Midwest Cast, and here we're ending the project with you. What that means is that we benefited, at least personally, when I was at the Institute of the Environment, I was invited to a workshop, which I believe was co-convened by USGS, Midwest Cast, and other partners in Wisconsin. And this workshop focuses on how do we think about the impact of extreme precipitation in the basin. And obviously, coming from a natural capital background, one area of interest was, for me, what is nature's contribution to reducing that increased precipitation that we experience now, but also the projections on precipitation is likely and very well projected to be high. So we benefited from a mini grant, actually about 15K, that led to a co-design project. So we had a bunch of stakeholders invited to the Institute of the Environment. We went through a 2-day workshop and came up with a project design. That project has, again, been funded by the Midwest Climate Adaptation Science Center. So that's the background. I always wanted to say that because this is the people's project, it is a project that has been designed by the stakeholders. In fact, a multi-stakeholder project. It's always amazing, and in our view, always useful to hear and share feedback, hear from you, but also share the feedback on the progress that we've made over the last 2 years. That makes it also critical to inform you that under this project, in every 6 months, we do a massive multi-stakeholder workshop where we present on the preliminary results and take stock of people's feedback and iterate on the work that we do and then deliver a better result in the subsequent workshop. So we just had our final stakeholder workshop last week, and I think it was very interesting from what we've had from the stakeholders and the feedback. So what is the project? The overall project, high level, is that what is that magnitude of nature's contribution in reducing flood risk? The question is not that nature does not contribute. The question is how much does nature contribute? And then from the perspective of this project and the work that we do here in the Department of Applied Economics under the Natural Capital portfolio, is that not only we think about nature's contribution to flood risk reduction, but also what are the multiple core benefits that nature offers. So today's presentation will only focus on flood risk, but if you are curious about what are the other contributions that nature offers for building resilience and reducing risk, we have a number of results on that. We will call it in our language multiple core benefits or ecosystem services that you get from having natural infrastructure in place. So if I can move to the next slide. So one key important aspect of this work is that it is a multi-scale analysis, meaning that from the lowest level here, we're talking about census tracts, we do have results that you can relate to depending on the scale at which you or your organization is working at. So from census tract, we can also have results for you at city level, at county level, and then state level. Of course, the geography of focus here is the Upper Mississippi Basin, which means that we have some states that have a small fraction of their boundary within the Mississippi, and some states that have a larger or more fraction of their coverage within this geographic boundary. It is important that when we think about this project, we think about the cross-boundary and the interlinkages that are important for resource management, but also from a watershed point of view. It's always important that I always say water doesn't know your state boundary, it doesn't know your regional boundaries. It just follows a hydrologic process, and that is very central to this project. Of course, a project like this cannot be led by just one person. It's the people's project, which means that, in fact, one of the critics, or well, not critics, but reviews that we got when we were formulating this project was, "Your team is so many, Famara. How are you going to manage all these people?" And we took that feedback very seriously, and we made sure that everybody on the project has their unique capacity contribution spelled out when we were revising the proposal. So that's the team. A lot of credit to this team, and many of them are within the university, but also you can see others that are not part of the university. They are critical partners to this project, like U.S. Forest Service, USGS, and then Rainbow Research, which actually has been, I would say, the twin partner for the project with the University of Minnesota, and then NCI, which is the Natural Capital Insights. So credit to this team. Obviously, credit to all of the institutions, the institute environment. That's where it all started. Credit to Rainbow Research, and again, all of these partners and Midwest Cast that have been supporting and advising this project. So today's presentation, the framing today is that we have an incredible infrastructure, which is called nature, and we're looking at what is nature's contribution for flood risk reduction. And what we try to do here is to do a scenario-based modeling using two different flood designs, return periods, storm designs. So you have a 50-year storm and a 100-year storm under alternative natural infrastructure and climate feature scenarios. So we've got about 5 different scenarios if you think about it. The alternative natural infrastructure are 3 scenarios, and your future climate scenarios are 2, which is also compared to the historical climate, and that makes it 6. The unit of analysis for this modeling is at HOC 6 level. Within the Upper Mississippi Basin, we have 17 of those. And for the key model that was run for this project, we had to run the model for 306 times to make sure that we have high resolution results at that level. And again, the results cuts across all of these geography or boundaries that may be of interest to different stakeholders, interstate level comparison, county level comparison, census tract, and all of that. There is one key question on top there, and I want you to take note of that because we may have a quiz at the end to ask you, under our restoration or our enhancement scenario, approximately how much additional stormwater does the current landscape store? This may be a question. So here we have it in gallons. So how many billions or millions of gallons of water is that? So the premise of the work, as I said, first we need to define, for basic understanding of all of us here, what is natural infrastructure and what is nature-based solution, because these two terms can be interchangeably used, but for the purpose of this project, and from our understanding, natural infrastructure comprises natural and restored ecosystems that are offering infrastructure scale services almost every day, in most cases for free, and in many cases, silently, in a way that many of us do not notice. Whereas nature-based solutions are the actions that are taken to protect, restore, and manage, or in some cases, even to create that infrastructure to address our societal challenges, including flooding, but also many other societal challenges that we all face. So this is really important. And I have two AI-generated results to show you, visually, what does this really look like? So natural infrastructure, on the left side, you can see these are the type of infrastructure when we say natural infrastructure for flood mitigation. These are the types that we think about. And then the right, you have the nature. But many of us, when we picture flood protection, most of the time we picture the built environment, the drainage, the levees, and all these things. But yet, we often ignore or forget that wetlands store gallons and cubic meters of water. We have floodplains that spread that water in a way that it helps to mitigate running that risk into communities. We have forests that also reduce that runoff, and healthy soils that absorb that every day. So from our project's point of view, we treat these ecosystems the way we would like to treat drains and the levees that we have. So what is the key message? That nature, from our perspective and from the analysis of this project, is a core infrastructure, not just a core benefit for flood mitigation or for flood management. As I said, your study area is the Upper Mississippi Basin. What makes this important is that we're taking a regional approach, both not just local, but also more regional approach than local, I would say. But we have results that speak to some of the local realities. But again, thinking about it from a regional point of view is important. And if you ask many people, we remember the Upper Mississippi Basin to cover 5 major states. But then again, as I said, some of the other states also have their boundaries included in that basin. So from this study, we have 10 states that are included in our analysis, and I will show you the names of all of those states. It is critical for, I don't think for this audience, many of you may know that this is an important economic, commercial, region for the US economy, for the Midwest economy, for trade, for agriculture, for water supply, for cultural connection. And there's a lot of relationship many of you have with this basin. And we've had report cards like the one that is being generated by the America's Watershed saying that this basin is rated at C. Many of the others within the Mississippi Basin, other sub basins are also rated as C, but that is concerning. That means that we got to do something about how we manage the basin. The problem we face today, the basin is entering a new flood regime, one that historical records show that, in fact, it wasn't immune to disasters. Heavy rainfalls, increased precipitation. One event in 1993 showed us that one event could destroy over 1,000 levees, according to the Army Corps of Engineers, and that could cost us billions of dollars. And increasingly, we've seen more disasters occurring or flooding occurring across the basin. So FEMA predicted or data suggests that the annual expected damage from just riverine flooding across the basin could be up to 340 million. That's a lot. And the National Climate Assessment also's prediction about the Midwest was clear that we could see a rise in heavy precipitation events in this region between anywhere between 37 to 45%. I think that is concerning. So that means that the future flood regime would definitely not look like the past. So we must think about how do we think about a storm design, infrastructure design that takes into account that additional water that is expected. So what's the ultimate damage, economic damage that the basin experiences? According to FEMA's data, this, if you add all of the about 17 hazards that the basin is affected by, it could be up to 4.1 billion annually is the expected annual loss from multi-hazard point of view. So that's a lot. But if you think about it, from a single hazard, which is the hazard of interest for our team, is the flooding. And here we're talking about riverine flooding. One key message that this project is trying to add value to what FEMA has already done is that where the dollar and where the so-called economic losses are may not necessarily be where the risk is. And I want us to take note of that. Where the dollar is may not always be where the most impact to the communities are. Because the dollar is an economic metric. It's taking things like the value of properties and other things that actually do not necessarily correlate with who is most vulnerable. It doesn't give us an equity lens in the analysis. So this is why, again, the need for doing this project. How do we adjust on what FEMA has done to say more about why flood hazard does not equate to flood disasters? To know this, we have used a framework that has been adopted by the IPCC and also been internationally recognized called INFORM. INFORM basically tells us that two communities can face the same water depth, yet they suffer different outcomes when it comes to impact. Why is this the case? Because of these three components. We look at the hazard exposure. how severe the flooding is and who lies on its path. That who lies is also the people, the assets, including the agriculture, the buildings, and other things. But the vulnerability, how susceptible are the people? What are the poverty rates, the age, the social, all the other socioeconomic differences that communities face and experience is really important to addressing the underlying root causes of disasters. So capacity or its lack of. Here we frame it as lack of coping capacity, how limited the communities are in their ability to prepare, to respond, and but also to recover from these disasters. So it's important that we think about risk from this interaction. The innovation and the added value of our project, many of the added values among them, is that we were able to integrate natural infrastructure, all of those things that I show you, into coping capacity dimension of this framework, so that we think of the wetlands, the floodplains, and then the forests as measurable flood risk infrastructure, not just scenery or just from a co-benefit point of view. And this we know from our basic hydrology that nature provided service for many, many decades, for many, many years, right? So it's important that we, so as I said, this is the framework. It's an interaction between these three components and inform. You can look at all of these international organizations today that are either supporting, using, and inform results to inform their risk management on the ground. The modeling methodology uh, could spend a lot of time on this slide, but because of the purpose of this audience, I don't know how we have a mixed audience, some maybe too technical, but I'll try to summarize what we try to do. So again, we have a unit of analysis, HUC 6, 17 watersheds, and we clearly sat down to look at how do we come up with natural infrastructure scenarios. And I'll explain that a little bit in the next slide, what each of those scenarios mean. And then we had the storm designs. We have a 50-year return period and a 100-year return period under a 24-hour storm, right? What's the amount of rainfall that you receive for each of those return periods within that time frame? And we have what we call the climate forcing or the rainfall forcing. Here you're talking about the historical rainfall as well as the projected rainfall that the area is expected to receive under two climate scenarios. And for the purpose of language and simplicity, we're going to say a moderate warming scenario, that is SSP2, 4.5, and then a high warming scenario, SSP5, 8.5. All right. Then we come to the core of our model. We had to think of a model that helps us to do a comparative analysis across our natural infrastructure in terms of these three outcomes. What is the total flood volume that we expect under each of the scenarios? What is the runoff retention volume? And then we have an index, which is the index that gets into the framework because this is an index-based approach, which is the runoff retention index. So again, you put all those together, you feed that into the next stage, which is essentially the interaction stage to look at hazard exposure, vulnerability, and coping capacity. So those are the three critical layers that we combine. So as I said, I promised to give you a little bit more information about the scenarios. So again, for the purpose of simplicity and in this interest of time, we're going to think of our existing natural infrastructure as the present day, and that is what it is, the present day baseline with the current curve numbers that the USDA Natural Resource Conservation Services has documented, and it's online out there. So this is our reference condition. We know where the degradations are. We know where the forest, all of the present day as is. And we build these two other scenarios. In our language, we call it a degraded natural infrastructure scenario. Mind you, it's the same land cover, but now there is an introduction of degradation of its condition. Wetland storage capacity will be limited. There's more degradation on forests and some degradation on grasslands. And again, with more expansion of impervious surfaces, especially in areas that are referred to as developed open space land cover types. So this is a wall, it's a feature where we think we really care about more imperviousness. So there is more concretes and other designs that are not taking into account the value of green infrastructure, and we call that a degraded scenario. And you have higher curve numbers from a hydrology language there. Under the restoration scenario, again, the same land cover, but now we have an improved condition or enhancement. Now you're thinking about from some types of cropland changes, right? From maybe soybean to some perennial crops, and you're thinking about some revegetation. And for the open developed areas, you're thinking about green infrastructure instead of gray or more imperviousness. One important caveat here is that for the wetlands and the forest, we do not touch them under restoration, even though people will often think, oh, when we are restoring the wetlands. And no. This is the most conservative approach we can take. Okay, we do that for a purpose. What we do is that for the mixed forest areas, we enhance some of that restoration. But for forests and wetlands, because we wanted to be able to compare this scenario to a scenario that is degraded with forests. So this is very important. It's also important to just clarify very quickly, not spending too much time on that, things that we didn't do. So we didn't do any site-specific design or feasibility or any costing in this project. We didn't do any economic costing and integration of additional core benefits from nature into it inform. No, we didn't do that. We only had flood as the only benefit to the inform index. So in fact, we get better results if we add all the additional benefits that nature offers under capacity. But we're not doing that. We just want the most conservative approach. And that, again, is for the purpose of feasibility and from a policy point of view. We do not want to introduce expansion. We do not want to say you're going to convert this agricultural land to some developed area or to some forest area, because these are things that may not be very feasible, practically speaking. So we do not want to think demigod about we can change things when the policy is not within our house. So we wanted to use this to inform policymakers. Even if you take the most conservative approach, what values and what additional benefit do you see? And again, thinking of that from a conservative point of view. So let's go to the results, given that I'm almost halfway into the hour. Number one, climate change makes the storms wetter. The predictions that we saw is that compared to historical rainfall, we expect up to 27% increase in rainfall under the high warming scenario. This can be up to 14% under the moderate warming scenario. This is consistent across the different storm designs. So for a 50-year, you see more increase, and a 100-year, you see again more increase of rainfall. That's the major result on the climate side. On the nature side, finding number two, degrading nature amplifies flooding. Again, as I said, basic hydrology tells us that this is true. The question is how much. The how much question our model is able to give us in terms of differences in flood volume. So you can see for a degraded condition, you have the amount that is avoided. That's the additional water that is added, and then the additional water that is avoided on the restored scenario. So there is less water added to avoid basically to the flood volume under restoration. Again, a restoration with a very conservative mindset that it's more of an enhancement. And then if you degrade, you add more water. And again, hydrology tells us that this is likely the case. Finding number three, restoration builds that infrastructure at scale. It's a storage question again. And the survey question I'm going to throw to all of you, from an Olympic-sized swimming pool comparison, this is up to 139,000 swimming pool sizes. So do the math, calculate that, how many gallons will that be? That's basically the survey question. So for some of you who may be interested in these results from a gallon point of view, how many gallons of water that is. And again, the same, you see more of under restoration, you see stormwater stored is more under degradation. That storage is lost. We see a loss in storage, which means that more volume of flooding would be expected. Hydrology also becomes resilient. Basically saying nature changes the risk itself. It's not just that nature does only reduce the runoff, but if you think about it from an integrated modeling point of view, nature can contribute to the outcome of the total flood risk itself. So it's not just that it is reducing the hazard, but it can also contribute to that building that resilience and then protecting communities. The results that you see here, again, for the different scenarios, we're better off under a more enhanced, a more nature-based solutions compared to a degraded situation. But we're also a little bit better off today than if we make things worse. So that's the key message. We either stay as things are, keep the landscape as is, and avoid more degradation or more imperviousness, or we try to encourage more nature-based solutions to enhance resilience. Coming to the key findings on INFORM itself. First, on one of its components, which is the hazard component, that tells us that basically, if you compare our historical rainfall trend today to the projections under a moderate warming and a high warming, we see a consistent increase in risk. But the key message is that even under different return periods, the risk remains in the same counties. Consistently, we spot the major risk or the major hazard exposures in the same, I shouldn't use the word risk, but hazard exposures in the same counties, which is basically here from the ranking would be Alexander County, Pulaski County, and then Mississippi County. Those would be some of the counties that, but it's hard to see the names here, but the name in there is showing the ranking of the top 10 highest exposed counties to each of these storm climate scenarios. Under the second component of the INFORM framework, which is the vulnerability, who is most vulnerable when the waters arrive? Again, this captures the poverty and all these things. And what is important here to note is that flood risk emerges where hazard meets vulnerable people with limited coping capacity. That is the basic definition of what flood risk is. Where hazards and where the risk is where the hazard itself meets vulnerable people with limited coping capacity. Because sometimes you can have a scenario where the hazard meets people who are less vulnerable and they have enormous coping capacity. The impact is less. So we can all be in the same neighborhood. The data suggests that there will be water level will be up to this much, yet you have some houses that are not adversely impacted by that water level and some that are completely thrown away. This is why taking an equity-based lens and taking investments that prioritize and weigh poverty conditions, housing conditions, age conditions, and mobility is critical. So flood adaptation has to be and must be equity informed, not just from where the water level is highest. And I think we know this, but we are trying to show it from a data point of view. So if you put the third component in the equation, which is the third ingredient, I call it here, is basically the lack of coping capacity. And it's important I spend a few minutes here because what is happening here, there is a database which is called the Baseline Resilience Indicators for Communities. That includes 49 indicators, including social, economic, institutional, and infrastructure. And it's a very useful data. FEMA is using it in its national risk index. But when we investigated and studied this, with great credit to the University of South Carolina, it doesn't have enough on the nature side of the story. They did have like things like wetland and something like that. But we thought that we could do a better job to give a better coverage based on our models on nature's contribution as a coping capacity. And that is why we came up with these nature-based scenarios or natural infrastructure scenarios. And those get incorporated into this existing database to give us what we call here the combined. Now you have the social and the nature added together. You have the social baseline plus the ecological buffer. Again, hydrology, and all of us know that nature provides some buffer. But then why is it not in the equation? Sometimes it's a modeling question, sometimes it's a data question, sometimes it's because we don't have that information. So we provided that information in this analysis. So if you take all those three things together, you basically now have a final informed risk map. What are the key results? The nature-based scenarios signal a negative effect, basically, which means nature reduces risk. So it's not adding risk, it's reducing risk. Again, we know this and we can tell you how much is it reducing risk. And I think this is essential for policymakers to know where the hotspots are that nature is helping to reduce that risk and places that can be enhanced with their natural infrastructure to contribute to enhancing that risk reduction. So that's the key message here. You can see the top row, all of the red there is basically comparing our degraded, if we are on a worse off scenario, in our degradation scenario compared to present day, we see risk adding up. So that's why it's red. But if you do our restored or enhancement, most conservative thing that we can do that we're not asking too much for policymakers to do, it's not very costly, is showing us positive. Again, why the magnitude there is still looking small, because we do not want to impose things that may not be feasible on current landscape. So that's the key message that we keep. The climate signal is positive. So which means that warming lifts risk across everywhere, regardless of the return period. Here I'm showing you a map on the 50-year return period, but even on the 100-year return period is even worse. So basically, if you're comparing a moderate to a historical and to our high and our historical, we see those hotspots, and especially in the southern parts of the basin. So if you, those were changed delta maps, they are changed comparing things. Here is the map that shows the relative risk. Again, think of this as relative. It's looking at risk across the entire basin, but then you can also look at it from within the state to look at which counties within each state may have higher. So you think of it as relative and not absolute risk that we're looking at here. This is, again, for organizations that are thinking about transboundary and cross-state level interactions, this is an important message to have. So what is the honest caveat? When we got into this project, we thought nature would be super high. But again, we were careful to not impose too much nature-based solutions when we are not the policymakers and the feasibility may not be there. So we took a conservative approach, but then the results still suggest that nature slows the risk. It does not reverse it, though. It does not reverse it. In fact, the most important key message from our point of view is that if climate adds roughly 3 times more to flood risk than nature removes. So nature reduces the risk, but it does not cancel a warming climate. That is to say that if we continue emissions as they are, rainfall continues to increase, it doesn't matter how much natural infrastructure we have in place. It could be that sometime even the storm itself can overwhelm the infiltration capacity of nature. We see where wetlands get flooded and forest areas get flooded because the infiltration capacity, the saturation level gets to a maximum, and then no additional water could probably flow, or the storage there could be reduced. And this is an important message. Now, I'm going to spend 5 minutes to wrap up so we can have questions. Let's look at the geography of risk at state level. The average shows that across all states, Missouri seems to be highest at state level average. South Dakota, be careful there with the interpretation because it's just a small fraction of South Dakota is within the basin. But that fraction that is within seems to be having high hotspots when it comes to risk level. So on a state level average, states like Minnesota seems to be among the lowest. But again, take that with some caveats. And I will explain why I said that. The geography of risk at the county level is showing that instead of an average of about 2 out of a ranking of 10, now we are having an average of 6 for some of the counties, right? So, and you can see that basically what this is suggesting, if you zoom in to county level, to census tract level, you see the actual impact. The hotspots get higher scores. For example, a specific census tract in Alexander County almost got to 9 out of the point of 10. So these are where we were interested. Where are those hotspots, right? And again, this is comparing a feature under a 50-year storm. So if you zoom, the more you zoom in, the more the map becomes redder or higher in terms of risk. So here's a nice comparison of that in a box plot. Basically, state average. Again, this is the what you see with averaging. When you do state average, we see something like 2 point something. For example, in Illinois, we see 2.7. But if you go to Alexander County, we see an average of 6 or 6 point. And then if you go to census tracts within that county, you can go up to 9 points out of 10. So to say that the county and then the census tract results get to reveal the hidden hotspots that the state average basically hides. If you think about it, what is in the exposed counties? Think about the top 20 census tracts now within the states, not across the basin. You see a different picture. Within the states, if you take the top 20 counties in each of the states, Minnesota now tops in terms of population exposed, right? You look at it from a county point of view, the map changes again because the geography of the risk increases. And now you see states like Illinois and Indiana actually showing higher population exposed at the county level, top 10 counties. Go to building, Wisconsin shows up at the census tract level, and then county level, we still see Illinois and Indiana surfacing with high values of buildings. This is building value, not buildings expected to be damaged, it's the building value. And agricultural value, even though there's a small fraction of South Dakota here, but we see a lot of that small area seems to be places with high agricultural value. And land area, similarly. So these are the values. We wanted to look at what is there in these hotspots that we need to care about. And then we take FEMA's data again and say, what did we see in terms of the expected annual damage to those values in those hotspots? You go to the building level, at census tract level, Iowa seems to tell us that there's a lot of buildings exposed and population. This is the equivalent expected life of a statistical life is basically how many people are expected to die in each given year. And we see Illinois again showing higher values or higher loss of life at the census tract as well as at the county level. Similarly, agriculture. The last one is important because that adds everything, all of the things that we talked about, and the total expected economic loss. And census tract level within the states, we see Iowa and as the highest. So that is why, think of how the map is changing depending on what you're looking at, what you're valuing. Many of this is because they are looking at asset values and they're looking at things that are basically monetized and not the vulnerability and the capacity of those communities. We can correlate that to FEMA and say, this is in the interest of time, I'll skip this, but basically the correlation suggests that our hotspots, when we take into account vulnerability and capacity, do not seem to strongly correlate with the FEMA data that only mostly look at the economic expected damage. This is a key finding. But if you look at our hazard, we see a much higher correlation between our flood hazard and FEMA's flood hazard. So there seems to be, again, stronger than the total risk because this one does not take into account vulnerability and capacity. So what? Two strategies that we all need to think about. Basically, we are saying in our language, let's try to defend the hotspots in the southern area because those are places that need eminent and urgent, eminent risk and need urgent issues to. That's why if you look at the US, I think it's the Army Corps database on levees, there are a lot of levees existing in this area. For the northern part, I am not going to say the levees are not important there, but restoration has source to signal a higher return on investment. And not only for those areas, but also areas downstream that most likely potentially will benefit from that prevention of. So there's no single solution here. There has to be a complement between these two strategies here. So in other words, I would say we have results for different decision makers at different scales, and they can look at the decision differently based on what their organization or institution is working on. We can recommend by saying five things. Keep the downstream defense working in the southern parts. Let's keep all those levees there. Let's upgrade them. Let's maintain them. Second is to protect and restore the upstream. This is important not only for their benefit, but for the downstream benefit. And third, and most importantly, count nature as infrastructure in our decision making, in our planning and permitting processes. And then the fourth one is to bring the two together. Pair nature with gray. We're not suggesting that gray infrastructure shouldn't be there. And finally, let's design a feature that would take precipitation more seriously. So size the investment to the future climate that we would expect, not the historical one. And I'll stop here, but these are the key headline takeaways: that 27% increase, the volume of water could increase twice more if you degrade things, and you have a lot more water out there. And then the climate signal seems to suggest more impact than our conservative nature signal. I would stop the presentation here and see if there are any quick questions, and see we're running out of time. Thank you very much. And we do have a story map that has all of this data uploaded. We can share the link with everybody. You can interact with the data at the census tract level, all these different levels that we've talked about. Thank you very much. I yield.
Thank you so much, Famra. If folks want to come on camera and ask your question directly, you're welcome to do that. Please just raise your hand. Otherwise, we welcome you to put it into the Q&A function, and I'll read it from there. As you're thinking about those, I'm going to pull up that poll from earlier again, and you can see if you remember some of the numbers and context that Famra changed, if your answer is different than the first time around, or if it's the same, or if you didn't get a chance to answer it earlier. Just keep an eye on those millions and billions. The first two are in million gallons, and the second two are in billion gallons. Give it a few more seconds here.
Also, you know, if there are questions in the chat, or I'm trying to look for those. Stop sharing, I guess. It's good to see you, Jessica.
Here is the results. How did everybody do, Famra?
So the correct answer is D. That would be 92 billion gallons. And in the language of the swimming pool size, that is 139,000 swimming pool size. So do some other calculation. You can tell me if I'm wrong. Thank you very much for taking your time to consider responding to this question.
All right, I see one question or two questions in the Q&A actually. So I'll start it off with those. Again, folks, feel free to share them in the chat, in the Q&A, or raise your hand if it's a question you want to ask directly. The first one here is, how is coping ability measured and what are the criteria? Can you talk a little bit more about that factor?
Yeah, so that's a very important question. And when we talk about coping capacity here, again, it's based on resilience concept. So you have 49 variable indicators that are considered within that. So there are a lot of them. And it ranges from economic related, for example, percent of home owner occupied housing units, for example, percent of labor force employed, things like that, to social factors like percent of population born within the current resident, religious organizations per capita, social organizations per capita. Like all of those things are social relations and social connections that are important for capacity. And to things like institutional resilience angle, for example, number of or percent of population in communities covered by, this can be very basic, but citizen COP programs, dollars invested in a given community, right, to housing level infrastructures, number of a percent of housing units. So there's a whole database, and I can share this. It's actually in the annex of the presentation that show all of these indicators that are considered to be part of coping capacity. And the data sources are from the Americas Community Survey mostly, and few from FEMA, National Atlas, and then, but largely it's coming from credible national institutions that are generating this data. And if you ask the question on our side, adding nature into that equation is basically taking that hydrology lens that I showed you to know that we know that different landscape conditions infiltrate water differently, right? We know that from basic hydrology. So we took the curve number approach to basically show that in a map. And that curve number is also informed by the USDA Natural Resource Conservation Services. Thank you very much.
Yeah, Pamara, I have also shared the link of Inform showing different components. I think that will be useful.
Yeah.
Yeah.
Thank you.
There's a question from Jessica in the chat. Famra, curious if you would imagine that the results you showed today would be different in other regions, or would there be some fundamental similarities? Your thoughts on that?
It's a very important question. In fact, I think it's on one of our recommended next steps, particularly because it's a relative risk. I would love to do this for the entire basin, not just the upper basin. Because if you take the effect that may happen in other basins because of the hydrology, how the hydrological connections look like, I can, short answer to Jessica's question is that the results will slightly differ because the landscape conditions in each of these areas or regions may be different. And I think that is an important point to make. Often we see places that have high forest cover, places that have more natural landscape. These are places that sometimes can suggest that obviously from the hydrology side, these are places that we expect to see more infiltration. But again, it's not just the infiltration that determines the risk. You can have a big forest that has huge infiltration capacity, yet there are not many people living there. So meaning the capacity can be high, but the exposure of the people and the infrastructure there is limited. So the risk will not be that high because, again, there are not many people living there or buildings there. So we do not worry too much about these places. So, but you can have a place where there is less forest and, again, even less risk if other components of capacity is higher, like if they have better hardcore infrastructure, more of these other indicators that I mentioned. So in a nutshell, it will differ based on the data. Thank you for that question.
I just want to add that the underlying data is a flood map that was created using terrain-based methodology. So obviously, a different location will have a different terrain than the Upper Mississippi River Basin. So that underlying data will be different. So everything will be an offshoot of that underlying flood map that was used in the Inform framework.
I think we have a question from Rebecca. Thank you, Philip, for adding that. So we mentioned that restoring landscape, upland forest. What role do you think floodplains play? Floodplain forest restoration can. So floodplain forest restoration, I would imagine that these would be places that would be essential to have because you mentioned floodplains are useful natural infrastructure for flood mitigation. But again, it all depends on the connectivity and the hydrology because you can have a floodplain that is very much close to nearby community and that can be impactful. But generally, I would recommend restoration that can enhance and increase the storage capacity of floodplains. In this case, did we do that specifically for this project? The restoration scenario mostly covers others, but not wetlands and other floodplains. I think we covered mostly improvements in the mixed forest areas that we encourage some enhancement restoration. But yeah, I would suggest that plays an important and critical role.
We've got another question in the Q&A. Thank you. We're getting through quite a few of these, so appreciate your answers, Famara. You indicated increased precipitation in large events. What time of year were you seeing those in the modeling, and how would that affect the potential for flooding?
That is an important question. So on the predictions, this is based on the SSP predictions, and again, the moderate warming condition and then the high warming condition. So I think the timeline on this, I need to verify this. Philip, you can help me if I miss the timeline. I think this may be by 2050 or 2100. I can't remember to what point of the data we're looking at, but I know it's the two scenarios. Philip, do you remember the timeline on when yeah, so it has to be either 2100 or by 2050. We can verify this and get back to you.
I can't remember the timeline, but
yeah.
we are using what you call return periods. So if it's a 50-year storm, a 100-year storm, it's not tied to this season. It's just what do you expect if it was a 50-year storm. But again, that doesn't mean it takes 50 years for that storm to occur. It could be 50 years. You can have 50-year storms twice in a week even. But that's the amount of flood or precipitation is categorized as return periods. The probability that it will happen in 5 years, 10 years, 50 years, 100 years.
Yeah. Yeah, right. but I think that, yeah, it's right, and we will let you know on the. I think Ben may not be on the call, but we will have timeline on the predictions, so we can verify that. I just don't want to give you wrong information. Thanks.
Ellen, I see that you have your hand up. If you want to go ahead and ask a quick question, and then that'll be our last one for today because we are at time.
Oh, hello. I would just like to say first, fantastic presentation, tons of work done, super interesting results. I'm blown away. But I'd like to also just, I lived in Tennessee, and alongside where I lived was a lot of riprapping along the river banks, and this prevented natural flooding, which then impacted farmers and the quality of their soil over time. You know, those floods brought a lot of natural silt and so on, nutrients to their farmlands. So there has to be kind of a middle ground between flooding and riprap. And I guess I just would like to comment that I would love to see some kind of study that would show the benefits from flood reduction and having some kind of middle ground of some areas that can flood and the benefits to the rest of the area, the basin in risk reduction. And do you follow my drift?
Yes.
That would be fascinating. Anyway, I can see various spin-offs from this study. So I just hats off to you. And that was my question. It's about, valuation.
Yeah. This trade-offs are the critical, and I think that aspect on the valuation is a great comment. Yeah, I see we are on time, so I don't want to add more to that. It's a great comment.
All right. Well, thank you so much, Famara, for this presentation. Thank you, everyone, for joining us and asking great questions. We appreciate it. I just dropped a link for our next seminar in August into the chat if you'd like to join us there. Otherwise, enjoy the rest of your Mondays.
Thank you, everyone. Thank you. Thank you very much.
Thank you,
everyone.
All right. Thank you.